Complementary metal oxide semiconductor (CMOS) is a technology for constructing integrated circuits. CMOS technology is used in microprocessors, microcontrollers, static RAM, and other digital logic circuits. CMOS technology is also used for several analog circuits such as image sensors, data converters, and highly integrated transceivers for many types of communication. In 1963, while working for Fairchild Semiconductor, Frank Wanlass patented CMOS. CMOS is also sometimes referred to as complementary symmetry metal oxide semiconductor. The words complementary symmetry refer to the fact that the typical design style with CMOS uses complementary and symmetrical pairs of p-type and n-type metal oxide semiconductor field effect transistors for logic functions. Two important characteristics of CMOS devices are high noise immunity and low static power consumption. Since one transistor of the pair is always off, the series combination draws significant power only momentarily during switching between on and off states. Consequently, CMOS devices do not produce as much waste heat as other forms of logic, for example transistor logic or NMOS logic, which normally have some standing current even when not changing state. CMOS also allows a high density of logic functions on a chip. It was primarily for this reason that CMOS became the most used technology to be implemented in VLSI chips. The phrase metal oxide semiconductor is a reference to the physical structure of certain field effect transistors, having a metal gate electrode placed on top of an oxide insulator, which in turn is on top of a semiconductor material. Aluminium was once used, but now the material is polysilicon. Other metal gates have made a comeback with the advent of high-K dielectric materials in the CMOS process, as announced by IBM and Intel for the 45nm node and beyond. Technical details. CMOS refers to both a particular style of digital circuitry design and the family of processes used to implement that circuitry on integrated circuits. CMOS circuitry dissipates less power than logic families with resistive loads. Since this advantage has increased and grown more important, CMOS processes and variants have come to dominate. Thus, the vast majority of modern integrated circuit manufacturing is on CMOS processes. As of 2010, CPUs with the best performance per watt each year have been CMOS static logic since 1976. CMOS circuits use a combination of p-type and n-type metal oxide semiconductor field effect transistor to implement logic gates and other digital circuits. Although CMOS logic can be implemented with discrete devices for demonstrations, commercial CMOS products are integrated circuits composed of up to billions of transistors of both types, on a rectangular piece of silicon of between 10 and 400 square millimeters. CMOS always uses all-enhancement mode MOSFETs. Inversion. CMOS circuits are constructed in such a way that all PMOS transistors must have either an input from the voltage source or from another PMOS transistor. Similarly, all NMOS transistors must have either an input from ground or from another NMOS transistor. The composition of a PMOS transistor creates low resistance between its source and drain contacts when a low gate voltage is applied and high resistance when a high gate voltage is applied. On the other hand, the composition of an NMOS transistor creates higher resistance between source and drain when a low gate voltage is applied and low resistance when a high gate voltage is applied. CMOS accomplishes current reduction by complementing every N MOSFET with a P MOSFET and connecting both gates and both drains together. A high voltage on the gates will cause the N MOSFET to conduct and the P MOSFET to not conduct, while a low voltage on the gates causes the reverse. This arrangement greatly reduces power consumption and heat generation. However, during the switching time, both MOSFETs conduct briefly as the gate voltage goes from one state to another. This induces a brief spike in power consumption and becomes a serious issue at high frequencies. The image on the right shows what happens when an input is connected to both a PMOS transistor and an NMOS transistor. When the voltage of input A is low, the NMOS transistor's channel is in a high resistance state. This limits the current that can flow from Q to ground. The PMOS transistor's channel is in a low resistance state and much more current can flow from the supply to the output. Because the resistance between the supply voltage and Q is low, the voltage drop between the supply voltage and Q due to a current drawn from Q is small. The output therefore registers a high voltage. On the other hand, when the voltage of input A is high, the PMOS transistor is in an off state, so it would limit the current flowing from the positive supply to the output, while the NMOS transistor is in an on state, allowing the output from drain to ground. Because the resistance between Q and ground is low, the voltage drop due to a current drawn into Q placing Q above ground is small. This low drop results in the output registering a low voltage. In short, the outputs of the PMOS and NMOS transistors are complementary such that when the input is low, the output is high, and when the input is high, the output is low. Because of this behavior of input and output, the CMOS circuit's output is the inverse of the input. The power supplies for CMOS are called VDD and VSS, or VCC and ground depending on the manufacturer. VDD and VSS are carryovers from conventional MOS circuits and stand for the drain and source supplies. These do not apply directly to CMOS, since both supplies are really source supplies. VCC and ground are carryovers from TTL logic, and that nomenclature has been retained with the introduction of the 54C, 74C line of CMOS. Duality. An important characteristic of a CMOS circuit is the duality that exists between its PMOS transistors and NMOS transistors. A CMOS circuit is created to allow a path always to exist from the output to either the power source or ground. To accomplish this, the set of all paths to the voltage source must be the complement of the set of all paths to ground. This can be easily accomplished by defining one in terms of the not of the other. Due to the De Morgan's laws-based logic, the PMOS transistors in parallel have corresponding NMOS transistors in series, while the PMOS transistors in series have corresponding NMOS transistors in parallel. Logic. More complex logic functions, such as those involving an and OR gates, require manipulating the paths between gates to represent the logic. When a path consists of two transistors in series, both transistors must have low resistance to the corresponding supply voltage, modeling an AN. When a path consists of two transistors in parallel, either one or both of the transistors must have low resistance to connect the supply voltage to the output, modeling an OR. Shown on the right is a circuit diagram of a NAND gate in CMOS logic. If both of the A and B inputs are high, then both the NMOS transistors will conduct, neither of the PMOS transistors will conduct, and a conductive path will be established between the output and VSS, bringing the output low. If both of the A and B inputs are low, then neither of the NMOS transistors will conduct, while both of the PMOS transistors will conduct, establishing a conductive path between the output and VDD, bringing the output high. If either of the A or B inputs is low, one of the NMOS transistors will not conduct, one of the PMOS transistors will, and a conductive path will be established between the output and VDD, bringing the output high. As the only configuration of the two inputs that results in a low output is when both are high, this circuit implements a NAND logic gate. An advantage of CMOS over NMOS logic is that both low to high and high to low output transitions are fast, since the pull-up transistors have low resistance when switched on. unlike the load resistors in NMOS logic. In addition, the output signal swings the full voltage between the low and high rails. This strong, more nearly symmetric response also makes CMOS more resistant to noise. See logical effort for a method of calculating delay in a CMOS circuit. Example: NAND gate in physical layout. This example shows a NAND logic device drawn as a physical representation as it would be manufactured. The physical layout perspective is a bird's eye view of a stack of layers. The circuit is constructed on a p-type substrate. The polysilicon, diffusion, and N-wave are referred to as base layers, and are actually inserted into trenches of the p-type substrate. The contacts penetrate an insulating layer between the base layers and the first layer of metal, making a connection. The inputs to the NAND are in polysilicon. The CMOS transistors are formed by the intersection of the polysilicon and diffusion, N diffusion for the N device and P diffusion for the P device. The output is connected together in metal. Connections between metal and polysilicon or diffusion are made through contacts. The physical layout example matches the NAND logic circuit given in the previous example. The N device is manufactured on a p-type substrate while the P device is manufactured in an N-type well. A p-type substrate tap is connected to VSS and an N-type N-well tap is connected to VDD to prevent latch-up, power, switching and leakage. CMOS logic dissipates less power than NMOS logic circuits because CMOS dissipates power only when switching. On a typical ASIC in a modern 90nm process, switching the output might take 120 picoseconds, and happens once every 10 nanoseconds. NMOS logic dissipates power whenever the transistor is on. Because there is a current path from VDD to VSS through the load resistor and the N-type network. Static CMOS gates are very power efficient because they dissipate nearly zero power when idle. Earlier, the power consumption of CMOS devices was not the major concern while designing chips. Factors like speed and area dominated the design parameters. As the CMOS technology moved below sub-micron levels, the power consumption per unit area of the chip has risen tremendously. Broadly classifying, power dissipation in CMOS circuits occurs because of two components. Static dissipation, sub-threshold conduction. When the transistors are off, both NMOS and PMOS transistors have a gate source threshold voltage, below which the current through the device drops exponentially. Historically, CMOS designs operated at supply voltages much larger than their threshold voltages. A special type of the CMOS transistor with near-zero threshold voltage is the native transistor. Tunneling current through gate oxide CO2 is a very good insulator, but at very small thickness levels electrons can tunnel across the very thin insulation. The probability drops off exponentially with oxide thickness. Tunneling current becomes very important for transistors below 130 nanometers technology with gate oxides of 20A or thinner. Leakage current through reverse bias diodes. Small reverse leakage currents are formed due to formation of reverse bias between diffusion regions and wells and substrate. Contention current in ratioed circuit. Dynamic dissipation. Charging and discharging of load capacitances. CMOS circuits dissipate power by charging the various load capacitances whenever they are switched. In one complete cycle of CMOS logic, current flows from VDD to the load capacitance to charge it and then flows from the charged load capacitance to ground during discharge. Therefore, in one complete charge-discharge cycle, a total of Q equals CL. VDD is thus transferred from VDD to ground, multiplied by the switching frequency on the load capacitances to get the current used, and multiply by the average voltage again to get the characteristic switching power dissipated by a CMOS device. Since most gates do not switch at every clock cycle, they are often accompanied by a factor, called the activity factor. Now, the dynamic power dissipation may be rewritten as A clock in a system has an activity factor alpha equals 1, since it rises and falls every cycle. Most data has an activity factor of 0.1. If correct load capacitance is estimated on a node together with its activity factor, the dynamic power dissipation at that node can be calculated effectively. Short-circuit power dissipation, since there is a finite rise-fall time for both PMOS and NMOS during transition, for example, from off to on. Both the transistors will be on for a small period of time in which current will find a path directly from VDD to ground, hence creating a short-circuit current. Short-circuit power dissipation increases with rise and fall time of the transistors. An additional form of power consumption became significant in the 1990s as wires on chip became narrower and the long wires became more resistive. CMOS gates at the end of those resistive wires see slow input transitions. During the middle of these transitions, both the NMOS and PMOS logic networks are partially conductive, and current flows directly from VDD to VSS. The power thus used is called crowbar power. Careful design which avoids weakly driven long skinny wires ameliorates this effect, but crowbar power can be a substantial part of dynamic CMOS power. To speed up designs, manufacturers have switched to constructions that have lower voltage thresholds, but because of this a modern NMOS transistor with a fifth of 200 mV has a significant sub-threshold leakage current. Designs which include vast numbers of circuits which are not actively switching still consume power because of this leakage current. Leakage power is a significant portion of the total power consumed by such designs. Multi-threshold CMOS, now available from foundries, is one approach to managing leakage power. With MT-CMOS, high-fifth transistors are used when switching speed is not critical, while low-fifth transistors are used in speed-sensitive paths. Further technology advances that use even thinner gate dielectrics have an additional leakage component because of current tunneling through the extremely thin gate dielectric. Using high-K dielectrics instead of silicon dioxide, that is the conventional gate dielectric, allows similar device performance, but with a thicker gate insulator, thus avoiding this current leakage. Power reduction using new material and system designs is critical to sustaining scaling of CMOS. Analog CMOS. Besides digital applications, CMOS technology is also used in analog applications. For example, there are CMOS operational amplifier ICs available in the market. Transmission gates may be used as analog multiplexers instead of signal relays. CMOS technology is also widely used for RF circuits all the way to microwave frequencies, in mixed signal applications. Temperature range. Conventional CMOS devices work over a range of -55 degrees Celsius to +125 degrees Celsius. There were theoretical indications as early as August 2008 that silicon CMOS will work down to -233 degrees Celsius. Functioning temperatures near 40 K have since been achieved using overclocked AMD Phenom 2 processes with a combination of liquid nitrogen and liquid helium cooling. Single electron CMOS transistors. Ultra-small CMOS transistors achieve the single electron limit when operated at cryogenic temperature over a range of -269 degrees Celsius to about -258 degrees Celsius. The transistor displays Coulomb blockade due to progressive charging of electrons one by one. The number of electrons confined in the channel is driven by the gate voltage, starting from an occupation of 0 electrons, and it can be set to 1 or many.